Welcome to another deep dive today. We're gonna be tackling a paper about finding rational points on curves using something called ICO models. And,
Oh, wow.
Yeah, so you probably already know this, but finding rational points is really important in number theory. It's basically like solving these Diophantine equations.
Yeah.
Which have been a challenge for mathematicians for like centuries.
Oh, for a long time.
Yeah, and this research, it's kind of cool because it uses the geometry of the icosahedron.
Oh.
That 20-sided shape.
Right.
To try to help solve this.
That's pretty cool. And that's a pretty advanced shape, right? 20 sides.
Yeah. So I have to admit, I'm a bit puzzled. What does an icosahedron have to do with finding rational points on curves? It seems like a bit of a stretch.
Yeah. At first, you might think that, but there's actually a really deep connection. So the surface of an icosahedron, it can be described by these equations in four-dimensional space.
Okay.
So specifically, like sigma squared equals 0 and sigma to the fourth equals 0. Yeah, so these equations, they define a special surface. And the idea here is that we can take curves and embed them into this surface to create what they call an ICO model.
Okay, so we're taking a curve, which we usually think of as like living in two-dimensional space.
Right.
And we're lifting it up into this four-dimensional ICO world.
Right.
But how does that work? I mean, are we like stretching it, distorting it, like until it fits?
It's kind of more elegant than that. Okay. The way it works is that we use a really clever substitution of variables.
Okay.
So let's say we have a curve, and it's defined by some polynomial equation, like g of x, y equals 0.
Mm-hmm.
To create this ICO model, we introduce new variables like x0, x1, x2, x3, x4.
Oh, wow.
And we replace x and y in that original equation with certain polynomials in these new variables. So it's kind of like a change of coordinates, but it has a specific goal in mind.
Okay. So it's like translating like the language of our curve into the language of this ICO surface.
That's a great way to put it.
Okay, but why go through all this trouble? What's the advantage of working with these ICO models? Well,
the first big win is that any curve at all can be represented by an ICO model.
Really?
Yeah, that's what they call theorem A in this paper. So this means that we have this standard way to represent any curve using this ICO framework.
Oh, that's impressive. That means we can like study curves in this really unified way.
You're exactly right. Yeah. And this is where things get really interesting.
Okay.
Not all ICO models are created equal.
Okay.
There are what they call degenerate ones, and then there are non-degenerate ones.
Okay.
And the non-degenerate ones, they are the stars of the show.
Ah, so there's a hierarchy.
Yeah.
Even within these ICO models.
Right.
What makes the difference? What makes an ICO model degenerate?
Okay, so it boils down to the structure of the polynomial equations that define this ICO model. Remember, we have those Icothafos equations, and then we have this additional polynomial equation, which we'll call f equals 0.
Yeah.
So a degenerate ICO model, it has this specific condition where one of the diagonal coefficients of this polynomial f, it's 0. And this might sound a little technical, but it means that the model, it lacks a certain kind of robustness.
Can you give me like an analogy to help understand that? What do you mean by robust?
Sure. Yeah. Imagine you're building a bridge.
Okay.
So a degenerate ICO model would be like a bridge with some crucial structural element missing. Okay. It might look like a bridge, but it's fundamentally flawed.
So it's like a bridge that's going to like collapse under pressure.
Exactly. Yeah. So a non-degenerate ICO model, they're important for finding these rational points because of what's called theorem B.
Okay.
This theorem, it states that for a non-degenerate curve, we can map its rational points to another special space, the space of what are called abelian varieties.
Abelian varieties, that's a bit outside my area of expertise.
Yes.
Can you give me like a quick primer?
Sure. So think of abelian varieties like higher dimensional cousins of elliptic curves.
Okay.
And the crucial point here is that this space of abelian varieties, it's very well studied.
Okay.
And there are a lot of powerful tools for analyzing points within it.
So it's like we're taking a problem that's difficult to solve in one space, and we're moving it to another space where it might be a little easier.
Exactly. Yeah, and this mapping is called the Paršin construction.
The Paršin construction.
Yeah, it allows us to leverage all of our knowledge about abelian varieties to gain insight into the rational points of the original curve.
So if we can find like a non-degenerate ICO model for a curve,
Right.
then we can use this Paršin construction. We can kind of unlock all these tools.
Yeah, exactly.
to help study these points.
That's exactly right.
That's amazing.
Yeah, and they even go further. They explore how this ICO framework can be used to tackle a problem that's closely related to the famous Fermat's last theorem.
Fermat's last theorem, that's a classic.
Yeah.
You're talking about the equation x to the n plus y to the n equals z to the n, right?
Exactly, yeah.
Mathematicians spend centuries trying to prove that there are no solutions for n greater than 2.
Exactly. And so
Integer solutions.
Yeah, integer solutions, yeah. And this paper, it explores a twist on that idea, looking at similar equations, but instead of being on the plane, they're on this ICO surface.
So instead of just x, y, and z, we're working with x0, x1, x2,
Yeah.
x3, x4.
Right, exactly.
That adds a level of complexity.
Yeah, it does, but the surprising thing is they were able to use this framework to make some real progress on this Fermat-like problem.
I'm really curious to hear more about that.
Yeah.
What kind of results did they get?
So they found that above a certain power, n, the only solutions to these equations on the ICO surface, they're what are called the trivial ones, which are easy to spot. What's even more exciting is they have this conjecture, they call it conjecture 9.2, that suggests that a similar Fermat-type problem can be solved for any variety, as long as it satisfies a certain condition related to how it intersects with a special set. They call it Z.
So they're basically taking this idea that originated with the icosahedron, and they're generalizing it to this much broader class of objects.
Exactly. Yeah, and this conjecture has the potential to really advance our understanding of these equations, these Diophantine equations.
This is all really fascinating stuff, but I think we've covered quite a bit of ground already.
Yeah.
Maybe this is a good place to pause and we can pick up the thread next time. There's still a lot more to unpack, like how these ideas play out in the specific case of plane curves. So join us next time for part 2 of our exploration of ICO models and rational points.
Sounds good.
Welcome back to our deep dive into the world of ICO models and rational points. In the last part, we talked about how these models kind of use the geometry of the icosahedron to represent curves in a new way. I was especially intrigued by the idea that any curve at all can be represented as an ICO model.
Yeah, it's a pretty amazing result, and it really does open up a lot of possibilities for systematically studying curves. But as we mentioned, the real breakthrough comes when we focus on non-degenerate ICO models.
Right. That's where the magic happens.
Yeah.
But to be honest, I'm still a bit fuzzy on how we actually determine if an ICO model is degenerate or not.
Okay.
It has something to do with that polynomial f that defines the model.
You're exactly right. Yeah. So remember the ICO model, it consists of the ICO surface equations, sigma squared equals 0 and sigma to the 4th equals 0. Along with this additional polynomial equation, which we've been calling f equals 0. So the key to determining the degeneracy really lies in the structure of this polynomial f.
Okay, so what are we looking for in f?
So we focus on what are called the diagonal terms of the polynomial.
Okay.
So these are terms where each variable appears raised to some power, but without any cross terms. So for example, a term like 5x0 cubed, that would be a diagonal term. But something like 2x1 times x2, that wouldn't be.
Okay, so diagonal terms are like they only involve one variable at a time.
Yeah, that's a good way to put it.
Okay, so how do these diagonal terms tell us if the model is degenerate or not?
So the rule is this: if there's any variable for which all of its diagonal terms in f have coefficients of 0, then the ICO model is degenerate.
So it's like each variable has to kind of pull its weight. If it doesn't show up at all in these diagonal terms, then the whole model is considered degenerate. I can see why that might be problematic.
Exactly, yeah. A degenerate ICO model, it lacks this kind of structural integrity, which makes it less useful for our purposes. It's like trying to build a house on a foundation of sand. It's not going to be very stable.
That's a good analogy. So we need to find a nice, solid, non-degenerate ICO model to help us find these rational points.
Right.
But how do we actually construct these models in the first place? I know you mentioned something called the Varieties embedding earlier.
Yeah.
But I'm not entirely sure how that works.
Right. So the Varieties embedding, it's a really powerful tool that allows us to map points from a lower dimensional space to a higher dimensional space.
Okay.
In a very specific way. So in the context of these ICO models, it's used to embed our original curve into that four-dimensional ICO surface.
Okay. So let's say we start with a curve in the plane, defined by some polynomial equation.
Yeah.
How do we actually use the Varieties embedding to lift it up into this four-dimensional world?
Okay, so imagine our original curve. It's defined by an equation like g of x, y equals 0. So the Varieties embedding gives us a recipe for replacing x and y with specific polynomials in those new variables we introduced, the x0, x1, x2, x3, x4. And these polynomials, they're designed to ensure that when we substitute them into our original equation, g of x, y equals 0, the resulting equation, along with those icosurface equations, it defines a curve that lives completely inside of that icosurface.
Okay, so it's like we're taking the coordinates of our original curve and we're transforming them into this new set of coordinates that fits nicely into the icosurface.
That's a great way to put it.
Okay, but how do we choose the right polynomials? It seems like there's like infinitely many possibilities.
Yeah, but the Varieties embedding, it gives us this very specific formula for these polynomials, and it's based on this idea of taking all possible monomials of a certain degree in the original variables.
Yeah.
And mapping them to monomials of a higher degree in the new variables.
Okay, so we're creating this higher dimensional representation of our curve that fits in nicely with the icon surface.
Exactly.
And then once we have that icon model, we can check if it's degenerate or not by looking at those diagonal terms in F.
That's exactly right.
Now, speaking of rational points, I remember you mentioned that the authors they applied this icon framework to this problem that's related to Fermat's last theorem.
Right.
Can you tell me a little bit more about that?
Yeah. So remember Fermat's last theorem. It deals with equations of the form x to the n plus y to the n equals z to the n. So the authors explored a similar equation, but instead of working in the plane, they worked in the icon surface. So they looked at equations of the form as 0 times x0 to the n plus a 1 times x1 to the n and so on up to am times xm to the n equals 0, where those x's are our icosurface variables.
Okay, so it's like we're taking the basic structure of Fermat's equation and we're transplanting it into this ico world. So what did they discover?
So they found that for large enough values of n, the only solutions to these Fermat-like equations on the icosurface, they're the trivial solutions, which are easy to identify.
Okay.
And so this suggests that the geometry of the icosurface is somehow constraining the possible solutions to these equations.
Yeah, seems like the shape of the icosahedron is playing a much bigger role than we thought.
Yeah, it's more than just like a scaffolding for these curves. It's somehow influencing the behavior of the curves and their rational points.
Exactly. And they take this idea even further. With their conjecture 9.2,
yeah.
They propose that this Fermat-like behavior, it extends to any variety at all, as long as it meets this certain condition about how it intersects with this special set Z.
Right, yeah. So the set Z, it's defined by a set of polynomial equations.
Okay.
And so the conjecture says that if the only rational points that lie in the intersection of our variety, and this set Z are what are called the trivial points.
Trivial points.
Yeah, then this Fermat-like result, it holds on that variety.
And by trivial points, you mean points that have simple coordinates or something like that.
Exactly. So the trivial points in this context, they're the ones where all of the coordinates they're either -1, 0, or 1.
Okay.
And so if the intersection of our variety with this set Z, it's well behaved in the sense that it only contains these simple points, then we can expect a certain type of behavior when it comes to solutions of these Fermat-like equations.
So it's like a test of compatibility. between our variety and this set Z. If they intersect in this nice controlled way, we get these really cool results about these Fermat-like equations.
Exactly, and this conjecture, it has the potential to really open up this whole new avenue of research in number theory, connecting the geometry of varieties to the solvability of these equations, these Diophantine equations.
And this is all really fascinating. We've come a long way from the construction of these ICO models to these really surprising connections to Fermat's last theorem.
Yeah, it's been a pretty amazing journey.
But I'm really eager to see how these ideas play out in the more familiar world of plane curves.
Right.
I believe that's where we're headed next.
That's exactly right. Yeah. In the next part, we'll explore how this concept of non-degeneracy applies specifically to plane curves and how it can be used to unlock these powerful tools for studying their rational points.
Welcome back to our deep dive on ICO models and rational points. We've been on quite a journey so far, exploring how these models use the geometry of the icosahedron to represent curves and solve problems in number theory.
It has been quite a fascinating exploration, and now, as promised, we're going to bring things back down to earth a bit and focus on how these ideas apply to a very familiar type of curve, plane curves.
Plane curves, yeah, that's definitely a comfort zone for me.
Yeah.
They're so fundamental to algebraic geometry, and yet they can still be so surprising sometimes.
That's true, yeah, and this paper really, really highlights that. It delves into the question of when a plane curve is non-degenerate, meaning that it has at least one non-degenerate ICO model. And remember, those non-degenerate models, they're our gateway to the Paršin construction and all those powerful bounds on the height of rational point.
Right. Non-degenerate models are the key to unlocking all those amazing tools to study rational points. And I recall the authors, they introduce a specific criterion for determining if a plane curve is non-degenerate. They call it criterion tau, I think. Or can you tell me a bit more about how that works?
Yeah, so criterion tau, it's based on a map, also called tau, that takes points from our familiar 2D plane and maps them onto the surface of our four-dimensional ICO surface.
So it's another one of those mapping tricks, taking points from a lower dimensional space to a higher dimensional space.
Yeah, there's definitely a theme emerging here.
Yeah.
And so the criterion itself is remarkably simple to state. If the image of our plane curve under this map tau avoids certain special points on the ICO surface, then the curve is non-degenerate.
Wow, it sounds almost too good to be true.
Yeah.
We just avoid a few bad points and we've got a non-degenerate curve. What are these bad points and what makes them so detrimental?
Yeah, so these bad points, they have a very specific geometric interpretation. They correspond to degenerate configurations of 5 points in the plane. Degenerate
configurations, I'm not sure I follow. Can you elaborate on that a little bit?
Yeah, so imagine you have 5 points just scattered in the plane.
Wait.
If 4 or more of those points happen to lie on a single line,
okay,
that's considered a degenerate configuration. It's like those points aren't being very adventurous. They're sticking too close to this one line instead of spreading out and exploring the whole plane.
So degenerate configuration is like a lack of diversity in how those points are arranged.
Exactly, yeah. And the bad points on the apparent surface that our curve needs to avoid, they correspond precisely to these degenerate configurations of 5 points in the plane.
So it's like a test of how well-behaved our curve is.
Yeah.
If its image under this map tau avoids those bad points, it means the curve itself is kind of avoiding those degenerate configurations.
Precisely. And the implications of this are huge. If a plane curve satisfies this criterion tau, we're guaranteed to be able to find a non-degenerate ICO model for it.
Right.
And then that opens up a whole world of possibilities.
Right. We get access to the Paršin construction. We get those bounds on the heights, all these tools for understanding rational points.
It really is like this treasure chest of tools that opens up for us.
Amazing. And it all just comes down to the geometry of the curve, how it distributes its points in the plane.
Exactly.
That's incredible that such a simple geometric criterion can have such profound implications for number theory.
Yeah. It's a really beautiful connection between geometry and number theory. But what if a curve doesn't satisfy this criterion tau? Is it a lost cause? Are there other ways to determine if it's non-degenerate or not?
That's a great question. And Not necessarily. Criterion tau is very powerful. But it might not be the only tool that we have. The authors of this paper, they mention that there might be other more subtle criteria for non-degeneracy that could be explored. So it's possible there are these other hidden patterns, other tests of how the points are arranged. That could tell us whether a curve is non-degenerate or not.
Exactly, and this opens up exciting avenues for future research. Mathematicians can now go and explore all sorts of different criteria, looking for new ways to identify these non-degenerate curves and unlock all the powerful tools associated with them.
This whole concept of ICAL models has really opened up my perspective on how we can study curves and their rational points. It's like we found this hidden structure, this icosahedron, lurking in the background that can guide us towards these new insights.
Yeah, it really is. It's a testament to the power of geometry as a tool for understanding these problems in number theory. And it really highlights the interconnectedness of mathematics, how these seemingly completely disparate areas can come together in these unexpected and beautiful ways.
We've reached the end of our deep dive. We've explored ICO models, their construction, their connection to Fermat's last theorem, and even their application to plane curves.
It's been quite a journey, but hopefully you've come away with a deeper appreciation for the beauty and depth of this area of mathematics and the power of these ICO models.
I certainly have.
Yeah.
And who knows what other mathematical treasures are out there just waiting to be discovered. Maybe there are other geometric shapes, other hidden structures that hold the key to unlocking even more secrets about the world of numbers. That's the beauty of math. It's an endless exploration.
I couldn't agree more. So to all our listeners out there, keep exploring, keep questioning, and keep the mathematical spirit alive.
All right, ready to dive into this paper on rational points. It gets pretty deep, but the ideas are really interesting. It's all about curves and their rational points.
Oh, yeah, those points where the x and y coordinates are both fractions.
Exactly. And this method they're using, these ICO models, seems like it might let us understand a lot of curves all at once.
Yeah, by connecting them to a special surface.
Okay, I'm hooked already. So the paper starts off tackling something that feels kind of related to Fermat's last theorem, that whole a to the n plus b to the n equals c to the n thing.
Right, where you can't find 3 positive integers that make it work when n is bigger than 2.
Exactly that.
Well, this paper, it kind of generalizes that idea to any rational surface. But instead of trying to actually find those solutions, they're trying to show that eventually the only solutions are, well, trivial, they call them.
Trivial?
Yeah, like just combinations of negro 1, 0, and 1.
So they just get predictable after a point.
Exactly. And to do this, they use this new type of Paršin construction.
Okay, whoa, hold on. Paršin construction.
Well, it's basically a way to take the rational points on a variety and map them to points on a moduli space of abelian varieties.
Moduli space, abelian varieties. Those are pretty complex ideas. Can you unpack those a bit?
Sure. Think of a moduli space like a catalog of mathematical objects. They all have similar properties.
Okay, like a catalog of what exactly?
In this case, we're talking about abelian varieties. They have this interesting group structure that makes them really fascinating to study.
Okay, I'm vaguely remembering something about those from algebraic geometry. So we map the rational points to this moduli space, but why? What's the advantage?
Because we already know so much about moduli spaces, there are some big theorems like Faltings theorem.
Faltings theorem.
Yeah, and it tells us certain sets of points on these moduli spaces are finite. So if we can cleverly map our rational points to one of those finite sets, boom, we've proven that the set of rational points on our original variety is also finite.
So we're kind of piggybacking on existing knowledge about moduli spaces. Clever. But this paper isn't using just ANOY Paršin construction, right? This is where those ICO models you mentioned come in.
You got it. The paper uses a totally new type of Paršin construction that relies on these ICO models.
All right, I'm all ears. What exactly is an ICO model?
Picture this very special surface called the ICO surface.
Okay, got it. A surface.
And it's defined by a couple of equations. Sub 2 sub equals 0 and sub 4 sub equals 0.
Equations, right. But what are those things?
They're called symmetric polynomials, but the specifics aren't super important right now.
All right, so a special surface defined by equations. How does this connect to curves?
Well, an ICO model is a way to take a and y curve and represent it as a curve on this ICO surface.
Wait, A and Y curve? Really?
Yep. And the paper actually proves this. It's theorem A. Every integral curve, a curve defined by polynomials with integer coefficients, has an ICO model.
That's kind of mind-blowing. You're saying no matter how squiggly and weird my curve is, there's a way to represent it on this specific ICO surface.
That's the cool part. And this lets us use what we know about the ICO surface to understand curves and their rational points.
So it's like a translation, turning a problem about a degree curve into a problem about this specific surface that we know more about.
Exactly.
But you mentioned earlier that not all ICO models are equally useful. Something about them being non-degenerate.
Yeah, that's crucial. While every curve has an ICO model, not all of them are non-degenerate, and those are the ones we want to focus on for the really powerful results.
Okay, so what's the difference? What makes an ICO model non-degenerate?
It's a bit technical, but basically the non-degenerate ones avoid intersecting with certain special points on the ICO surface.
And why are those special points so bad?
Think of them like singularities, places where the surface isn't totally smooth.
Okay, so those points mess things up.
Exactly. The properties we need to make our techniques work don't always hold if the model is degenerate.
So they're like glitches in the system. So the paper must address this, right? Which curves actually have these good non-degenerate ICO models?
Right. They give some answers. For instance, they show that a general ICO model, meaning most of them, will be both non-degenerate and smooth. They even have a formula for the genus of these models. It's 2 plus 1 sup 2 sup, where n relates to the degree of the model.
Okay, so we've got these ICO models, and the non-degenerate ones are the key. But what kind of insights do we get from them?
Well, that brings us to theorem B, which is where things get really interesting for number theorists. It says that for curves with a non-degenerate ICO model, there exists an effective Paršin construction.
Effective Paršin construction. Okay, break that down for me.
It means we can actually construct the mapping between the rational points on our curve and then certain points on the moduli space. It's not just a theoretical existence, we have a method to build it.
Oh, so it's practical, not just theoretical.
Exactly.
And what about the Paršin construction part?
Right, and it's a special type called a GL2 type construction.
GL2 type. Another new term.
Don't worry too much about the details, but basically it means the abelian varieties we end up with on that moduli space are very well studied, so we can use existing knowledge to understand our rational points even better.
So even more piggybacking. I like it. But how does all of this help us understand those rational points? Proving that they eventually become those trivial solutions.
That's where the effective Mordell conjecture comes in.
The effective Mordell conjecture.
Yeah, but to explain that, we need to talk about the height of a rational point.
Height, as in how tall it is.
Not quite. It's a way of measuring how complex the fractions are in the coordinates of the point.
Okay, so simpler fractions mean lower height.
Exactly. And the effective Mordell conjecture aims to prove that there's a limit to how high the height of the rational points on a curve can get.
So we're not just saying there are finitely many rational points, but that we can actually put a limit on how complex they can get.
Precisely. And this paper gets us closer to that. Corollary 7.5 gives an explicit bound on the height of rational points for curves with those good non-degenerate integral ICO models.
Wow, so we're going from abstract existence to concrete calculations? That's impressive. But the really cool part is that this applies to a lot of curves at once, right?
You got it. The bound only depends on a small part of the equations that define the ICO model. So many curves can share the same bound.
That's really powerful. The paper also mentions something about plane curves satisfying a condition they call. What's that all about?
Oh, that's a good example of how they apply this to specific families of curves. Condition ensures that the curve, when projected onto the ICO surface, avoids those problematic special points we talked about.
So it's like a guarantee that we're dealing with a non-degenerate ICO model.
Exactly. And that lets them get an even cleaner height bound. It's corollary 8.1 in the paper.
This is all starting to feel beautifully interconnected. Eco models, moduli spaces, Paršin constructions, heights, it's all coming together to help us understand these rational points.
Yeah, and the paper hints that there could be tons of curves out there that satisfy this condition, so this method could have a huge range of applications.
Okay, my brain is definitely full.
But that's what makes this so fascinating.
Absolutely. Before we dive even deeper, can you give us a little recap of the most important takeaways so far?
Sure. It's all about using this connection between any curve and its ICO model on this special surface. And that gives us real concrete tools to understand those fascinating rational points on curves.
And we're not just talking theory. We're talking explicit constructions, height bounds, real applications.
Right. It's the combination of deep theory and practical results that makes this paper so exciting. We have effective Paršin constructions, explicit height bounds, and the potential to use this for so many curves.
Amazing. It's incredible to think that something as simple as a point on a curve can lead to such deep and complicated math. But before we move on, I have one last thought for our listeners to ponder.
Ooh, I love a good cliffhanger.
Could we use similar techniques, with special surfaces and mappings, to solve other problems in number theory? Maybe some of those big mysteries that have stumped mathematicians for ages.
No, that's a great question. And honestly, I think the answer is yes. Who knows what other mathematical treasures are out there just waiting to be found? As we go deeper into all these constructions and theorems, I keep thinking about the history of all this. It's like we're building on the work of so many mathematicians who came before us.
Yeah, for sure. This paper's built on centuries of progress. It's like a culmination of all these brilliant minds tackling these fundamental questions. Like, what were some of the key moments that led to this research?
Well, you can't talk about this without mentioning Faltings' proof of the Mordell conjecture back in '83. It was a huge deal. It proved that certain curves have only finitely many rational points.
Right, a big theoretical breakthrough.
Exactly. But it didn't really tell us how to actually find those points or how many there might be.
So we knew they existed, but not much else.
Yeah. And that's where this whole quest for effective results comes in. People wanted to go beyond just proving they're out there and actually calculate things, make predictions. This paper is a big step in that direction.
So it's like going from knowing something exists to figuring out how it works.
Precisely. And another important piece is the development of the theory of moduli spaces.
Moduli spaces, right. Those catalogs of mathematical objects.
Yeah. They've become so powerful in algebraic geometry and number theory. They let us organize all these complex things, see connections and patterns.
Like having a well-organized library.
Yeah.
You can find what you need easily.
Perfect analogy. And then there's the idea of Paršin constructions, which bridge the world of rational points and moduli spaces.
Paršin constructions, yeah, those mappings that let us translate problems about rational points into questions about moduli spaces.
Right. They let us use what we already know about moduli spaces to understand rational points. And this paper comes up with a whole new type of Paršin construction using those ICO models we discussed to provide a new perspective on these classic problems.
So it's like they're using new tools to solve old problems.
Yeah.
But can we go back to ICO models for a second? Where did that idea even come from, representing curves on that specific surface?
Oh, it's a cool story that actually goes back to the 19th century with mathematicians like Klebsch and Klein.
Okay, way back.
Yeah, they were studying icosahedra, these 20-sided solids with all those beautiful symmetries.
Oh, yeah. Lots of triangles sitting together.
Exactly. And they discovered these amazing connections between icosahedra, certain equations, and surfaces. They figured out how to represent complex curves using simpler geometric configurations on what we now call the ICO surface.
So those ICO models aren't just something someone came up with randomly. They're rooted in this deep geometric history.
Right. And this paper takes those old ideas and applies them to the modern study of rational points. It's a great example of how mathematical ideas can evolve and find new uses in unexpected ways.
Like they were just waiting for the right time and the right tools to be useful. Okay, we've talked about history, motivation, big ideas, but I'm ready to see some actual math. Can we look at some of the equations and proofs that make all of this work? It might be challenging, but I think our listeners are up for it.
I'm always down for a math challenge. What do you want to start with?
Well, you said the I-core surface is defined by those two equations.
Yeah.
Sub 2 sub power is 0 and sub 4 sub equals 0. Can you remind me, what are those 6 things again? What's special about them?
Sure. Those are symmetric polynomials, meaning they have this special property. If you switch around any two of the variables, the polynomial stays the same.
Okay, yeah, I vaguely remember symmetric polynomials from algebra, but why are they important here?
Well, they're crucial for understanding geometric shapes, especially those with lots of symmetry, like our icosahedron. Those equations, sub 2 sub equals 0 and sub 4 sub equals 0, using those specific symmetric polynomials, they actually capture the essence of the icosurface's structure.
So those equations aren't just random. They're connected to the geometry of the icosurface, I see.
Exactly. And the paper uses that connection to prove theorem A, which says every integral curve has an ico model. Do you want to walk through that proof?
Yeah, sure. But go slow. It's a lot to take in.
No problem. It uses some clever algebra and a bit of geometric intuition. So you start with any integral curve, meaning it's defined by polynomials with integer coefficients.
Got it. Our curve has nice whole number polynomials.
Right. Now we need to represent this curve on the icosurface, which is defined by those equations with sub 2 sub and sub 4 sub. So we build a new set of polynomials from the ones defining our original curve.
So we're changing our equations to fit on the icosurface.
Yep. And the key is to make sure these new polynomials also satisfy those sub 2 sub equals 0 and sub 4 sub equals 0 conditions. That guarantees the curve they define is actually on the icosurface.
Okay, so we've transformed our equations, got a new curve on the icosurface, but how do we know this new curve is a good representation of our original curve?
That's where the magic of algebraic geometry happens. We can show there's this special map called a birational map between the original curve and this new one on the icosurface.
A birational map? Okay, that's a new one. What's that?
Imagine you have two curves and you want to compare them. A birational map connects them almost perfectly, except maybe at a few specific points, like saying they're basically the same, with a few tiny differences.
So even if their equations look different, the curves are basically identical.
Exactly. And that's what we prove in Theorem A. The original curve and its representation on the icosurface are birationally equivalent. They're essentially the same curve, just written differently.
Yeah, that's pretty amazing. It's like translating between two different ways of describing the same thing.
And that translation lets us use all the tools we have for studying the icosurface to understand rational points on any integral curve.
This is all starting to make sense. But you said not all ico models are created equal. Some are degenerate, and those aren't as helpful. What's the difference between a good, non-degenerate ico model and a bad, degenerate one?
Right. It all comes down to how the curve, when it's on the icosurface, interacts with certain special points. These points are kind of like singularities on the surface, places where it's not perfectly smooth.
Ah, like a sharp corner on an otherwise smooth surface.
Exactly. And a degenerate ico model is one that passes through one or more of these special points.
So why is that a problem? Seems like a small detail.
It might seem that way, but passing through these special points messes up some of the properties we need for our techniques to work properly. They're like glitches in the system.
So the good ico models, the non-degenerate ones, are those that avoid those tricky points.
Exactly. And that brings us back to those plane curves we talked about, the ones satisfying that condition. That condition is all about avoiding those special points, right?
Yeah. So it guarantees we're dealing with a non-degenerate ico model.
Exactly. And because we're working with non-degenerate ico models, we can apply those powerful theorems about moduli spaces and Paršin constructions to get those specific bounds on the height of rational points.
Wow. It's all coming together. Ico models, special points, condition in top, and the height of rational points. It's all connected.
And this is just the tip of the iceberg. This paper opens up so many possibilities for exploration. We can start asking similar questions about other surfaces, maybe even higher dimensional spaces.
It's incredible to think about how much is still out there to be discovered. But before we get lost in all the possibilities, I think we need a minute to process everything we've learned so far.
I agree. It's a lot to take in.
It is. One thing that's really striking me is how this paper brings together so many different areas of math. It's not just number theory. It's also deeply connected to algebraic geometry and even topology.
That's a great observation. It's like a mathematical melting pot, blending together different areas to create something entirely new. And you mentioned how the icosasurface has this fascinating geometric history linked to the symmetry of icosahedra. How does that symmetry show up in the equations and proofs?
That's a really insightful question. It's subtle, but the icosahedron symmetry is embedded in the icosasurface and its equations. Remember those symmetric polynomials, sub 2 sub and sub 4 sub? Those weren't chosen at random. They're carefully chosen to reflect the symmetry of the icosahedron.
So the choice of those specific polynomials is tied to the geometric shape we're working with.
Yes, and that symmetry has some big consequences. For example, it helps explain why every integral curve can be represented as an icosa model. The fact that we can represent any curve on this supersymmetric surface really shows the power of that underlying symmetry. So it's like the symmetry of the icosurface is organizing everything. bringing order to the chaos of curves and rational points.
I like that. It captures how symmetry can simplify things and reveal hidden connections. And that's what this paper does. It uses the symmetry of the icosurface to translate questions about rational points into the language of moduli spaces, where we have all these powerful tools.
It's like the icosurface is a lens focusing our mathematical vision on those elusive rational points.
That's beautifully put. And remember, we're not just talking about abstract proofs. This paper gives us specific constructions, bounds, and algorithms, all thanks to the power of symmetry and those clever mappings.
I'm starting to see how this research could go way beyond the specific problems they're looking at in the paper. It's like a blueprint for tackling other tough questions in number theory, using similar geometric approaches.
Absolutely. A great example is the Birch and Swinnerton-Dyer conjecture, which connects the number of rational points on elliptic curves to these things called L functions. It's a huge unsolved problem in number theory, and I bet techniques inspired by this paper could give us new insights into that conjecture.
Wow, using geometry and symmetry to attack one of the biggest mysteries in math, that's pretty exciting.
Right. It shows the power of thinking across different areas of math, combining ideas to create new insights and approaches. And I think this paper is just the beginning. We might be seeing a whole new era of math, where geometry and symmetry take center stage.
This has been an amazing deep dive. It's made me appreciate the beauty and power of geometry and how it connects to other parts of math in such surprising ways.
It really is. It shows how math can take us on these amazing journeys, uncovering hidden connections and helping us understand, the structure of the universe.
This whole idea of using ICO models to understand rational points is super powerful. But I'm wondering, how much of it is specific to the ICO surface itself? Could we use this method with other surfaces, maybe even higher dimensional things?
That's a great question, and a lot of mathematicians are working on that right now. The success of ICO models comes down to a few things.
Like what?
Well, first, the icosurface has that incredible symmetry we've been talking about that makes it possible to connect curves to their representations on the surface so nicely.
Right, it's like the symmetry gives us a framework to organize and understand the curves.
Exactly. Second, the icosurface has a fairly simple structure when it comes to its singularities, those special points that cause trouble for degenerate models.
So the non-degenerate models are easy to work with on the ICO surface because of its structure.
Exactly. Now, if we want to use this with other surfaces, we need to find ones that have similar features.
So surfaces that are both highly symmetric and have a manageable set of singularities.
You got it. It's not easy, but people are making progress. There are these things called K3 surfaces and Calabi-Yam manifold that have some similar properties to the ICO surface. They have a lot of symmetry, and we understand their singularities pretty well.
So maybe those could be the key to understanding rational points in even higher dimensions.
They very well could be. Mathematicians are actively researching that, seeing if we can build something like ICO models on these surfaces, and then, develop corresponding Paršin constructions and height bounds. It's a really exciting area with the potential to change how we understand rational points in higher dimensions.
It's mind-blowing to think about all the mathematical possibilities out there. It feels like we've just scratched the surface.
Absolutely. Every time we discover something new in math, it opens up a whole bunch of new questions and possibilities. It never ends. We're always pushing the limits of what we know and understand.
This deep dive has been incredible. It's given me a whole new appreciation for geometry and how it connects to other areas of math in such unexpected ways.
Me too. It reminds us that math isn't just a bunch of facts and formulas. It's a web of interconnected ideas, a beautiful structure, and a place where curiosity can lead to amazing discoveries.
On that note, we'll wrap up this episode of The Deep Dive. Thanks for joining us on this mathematical adventure. We'll see you next time for another fascinating exploration of the world of knowledge. All right, jumping right into it today, we've got some seriously fascinating math lined up. Our listener has sent over a research paper that's really pushing the limits in number theory. All about this clever geometric technique. It's called ICO models, and it's used to analyze those rational points on curves.
Yes, and this paper really digs into some classic problems, like trying to understand the solutions to equations. But not just any solutions. We're talking about those rational solutions, the ones that can be expressed as fractions.
Okay, so we're starting off with that age-old question, What are the solutions to these equations? And can we find the ones that are nice in the sense of being rational numbers.
Exactly. The authors, they're aiming to study these rational points, but not just one at a time. They're using the strategic method to construct special models of the curves inside a larger space called a moduli space.
Ah, so it's like building a framework. Right. To analyze these whole families of curves all at the same time. Instead of getting stuck with just one curve at a time, we're searching for a more global perspective.
Yeah, that's a great way to put it. And the type of moduli space they're focusing on is particularly interesting, these rational moduli spaces. They're spaces where each point actually represents a different abelian variety.
Oh, abelian varieties. Those are those geometric objects that generalize elliptic curves, right?
Yeah,
I'm sensing we're going to be diving deep into some algebraic geometry here.
absolutely. Abelian varieties, they've got this rich structure that makes them perfect for studying these number theoretic questions. And to connect those rational points on a variety to these points in moduli space, well, the authors, they use a technique called Paršin constructions.
Circular constructions.
Yeah.
They're like maps that link these seemingly different mathematical worlds, right?
Yeah.
Providing a way to translate information about rational points into the language of moduli spaces.
Oh, perfect analogy. Now, the real stars of this paper are those ICO models, specific types of models of curves, and they live within a particular rational moduli space. It's defined by the equations tau 2, 0, O plus 4 in a 5-dimensional projective space.
Hold on. 5-dimensional projective space. We're already in pretty abstract territory. But why ICO models? What's so special about that name?
Well, the name actually comes from the fact that this moduli space is deeply connected to the symmetry group of a regular icosahedron, one of the 5 Platonic solids. It's this beautiful connection between algebra and geometry.
Whoa, that's visually striking. I'm picturing a curve embedded in a space with icosahedral symmetry. This choice of moduli space must have implications for the types of curves they can study, right?
It does, and it leads to the concept of non-degenerate curves. Basically, a curve is considered non-degenerate if its ICO model avoids certain special points within the moduli space.
So it's like saying a non-degenerate curve is well-behaved,
Yeah.
in the sense that it doesn't intersect these problematic points within the moduli space.
But how do we know if a curve is non-degenerate in the first place?
That's a great question. One of the key results in this paper, which they call Theorem A, states that every integral curve over the rational numbers has an ICO model over the real numbers. Essentially, any nice curve. Okay, so Theorem A guarantees we can find an ICO model for any well-behaved curve. That's a great starting point. But how does this actually help us study those rational points we're after?
Well, the authors, they go on to show that for a non-degenerate curve, there's this special type of Paršin construction called an effective Paršin construction. What this means is the map not only exists, but it also has certain desirable properties that make it really useful for studying heights.
Heights, that's a new term for me in this context.
Think of the height of a rational number as like a measure of its complexity. For example, the fraction 12 has a smaller height than 130, 32, 5/6. And what's fascinating is that these effective Paršin constructions, they allow us to connect those heights of rational points on a curve to the heights of points in the moduli space.
So it's like translating the problem of understanding rational points into a whole new arena, the moduli space, where we might have more powerful tools at our disposal to analyze them.
Exactly. And this brings us to one of the most famous conjectures in number theory, the Mordell conjecture. Now, this conjecture was actually proven by Faltings, so it's a theorem now, but it states that curves with a certain level of complexity, well, they only have a finite number of rational points.
So not just a random scattering of rational points, but a finite, countable collection. That's huge. And I'm guessing this is where that ICO model approach comes in.
You guessed it. The authors are using this framework of ICO models and effective Paršin constructions to make progress on an effective version of Mordell. So instead of just proving that there are finitely many rational points, they're aiming to provide explicit bounds on just how complex those points can be, meaning how large their heights can get.
So it's not just knowing there's a limit, it's about understanding how big those rational solutions could actually get. That's a much stronger statement. What kind of results are they getting?
Well, they have a result called Theorem E, and it provides an explicit bound on the complexity of rational points on these non-degenerate ICO models. This bound involves a quantity they denote as ETH, which is calculated from the coefficients of the equations that define the ICO model. And what's interesting is that this quantity is independent of the degree of those equations.
Wow, so no matter how complicated those equations defining the curve, we have this explicit bound on the complexity of its rational points. That's pretty amazing.
Yeah.
But how do they actually apply this in practice? Do they have any specific examples?
They do. They provide some really concrete examples of families of plane curves, curves defined by equations in two variables. These curves are non-degenerate and therefore have those effectively bounded rational points. And to determine whether a given plane curve is non-degenerate, they introduce a criterion they call...
So it's like a checklist we can use to see if a curve fits the bill for this effective Mordell approach.
That's really cool. I'm seeing in the outline that they even connect this to Fermat's last theorem, which is probably one of the most famous results in number theory. How does that fit into all of this?
They apply their techniques to a problem called the generalized Fermat problem, which is a fascinating generalization of that classic Fermat's last theorem. It explores solutions to equations of the form a0x, 0 plus many, plus amxm equals 0, where the exponents are allowed to vary.
So instead of just xm plus yn equals, we're dealing with sums of powers with different exponents. Sounds complicated.
It is. They specifically study this problem on the icosahedron surface, which is another rational surface similar to the projective plane. And they actually managed to solve a version of the generalized Fermat problem on this surface by combining their height bounds with tools from Diophantine approximation. It's a field of mathematics that studies how closely you can approximate irrational numbers with rational ones. Wow, that's quite a journey, connecting ICO models, height bounds, and even Fermat's last theorem. It's amazing how this paper brings together so many different pieces of the mathematical puzzle. I'm eager to delve deeper into the specifics of their proofs, see how they actually construct these ICO models and derive those height bounds.
Absolutely. Let's take a closer look at those in the next part of our deep dive.
All right, so we've laid out the big ideas of this paper, using these ICO models to analyze rational points on curves, even tackling problems related to Fermat's last theorem. Now I'm ready to get into the details of their methods. Where do we start?
Well, let's jump into the heart of their construction, outlined in Theorem 4.1. This theorem really focuses on non-degenerate varieties within a larger moduli space. Remember, we're dealing with a variety M over those rational numbers, and it extends to a tame coarse moduli scheme over a specific base scheme.
Right, so we've got this moduli space M. It's like our catalog of different geometric objects, and we're zeroing in on varieties X within M that are non-degenerate, with respect to a compactification of M denoted by M.
Precisely. Now, Theorem 4.1 states that if X is non-degenerate in M, then we can find this open-dense subvariety U within X that inherits this special moduli scheme structure.
Okay, so we're starting with this well-behaved non-degenerate variety, and we can find this chunk of it, this open-dense U, that becomes a coarse moduli scheme itself. What's the significance of that?
Well, this structure is key because the forgetful map of this coarse moduli scheme U actually gives us a Paršin construction. This allows us to apply Faltings' theorem and conclude that the set of rational points on U, denoted UQ, is finite.
Ah, it's like a chain reaction.
Yeah.
Non-degeneracy leads to the coarse moduli scheme structure, which gives us a Paršin construction. And that ultimately leads us to the finiteness of rational points. It's a beautiful cascade of mathematical ideas.
Exactly. And what's remarkable is this theorem holds not just for those general moduli schemes, but also for these more specific Hilbert moduli schemes.
So this framework has a pretty broad range of applications then. That's great. But in that Hilbert case, I see that we actually get even more information, right? The theorem states that we can actually bound the height of each rational point in UQ, and even the number of those points. That's impressive.
It is a pretty powerful result. These bounds involve certain quantities related to the moduli space, like the discriminant of the number field underlying that Hilbert moduli scheme. But, to really appreciate the elegance of this theorem, let's dive into how they actually prove it.
Yes, let's get into the mathematical machinery. What are the key steps in their proof?
Okay, so the proof starts with a crucial observation. It's captured in Lemma 5.4, which states that non-degenerate models in M, they naturally inherit a coarse modular scheme structure. Specifically, any non-degenerate model in M extends to a proper coarse moduli scheme over a suitable base scheme. And importantly, this coarse moduli scheme has an empty branch locus.
Okay, empty branch locus. That sounds intriguing, but can you remind me what a branch locus is in this context?
Of course. The branch locus of a morphism essentially tells us where that morphism fails to be étal. In simpler terms, it's where the map isn't locally an isomorphism in a particularly nice way. Having an empty branch locus simplifies things considerably.
So this Lemma 5.4 ensures that our non-degenerate models have this nice property of an empty branch locus, making them easier to work with. But how do we actually connect this model back to that open-dense subvariety U, the one within our original variety X?
That's where lemma 5.5 comes in. This lemma provides the bridge, stating that if we have a monomorphism, essentially an injective map, from another scheme Y to Y, which is our coarse moduli scheme, then under certain conditions, Y also inherits a coarse moduli scheme structure.
So it's like this moduli scheme structure is contagious. It spreads from Y to Y through this special map. But what are those certain conditions that you mentioned?
These conditions involve either the flatness of that monomorphism or the tameness of the moduli problem. Flatness is a technical condition from algebraic geometry that, roughly speaking, ensures that fibers of the map behave, well, nicely. And tameness, in the context of moduli problems, well, it ensures that things behave well under base change, meaning when we switch perspectives, like when we look at the problem over different base schemes.
Got it. So we need these additional properties to ensure the transfer of the moduli scheme structure. And then how do we apply these lemmas to actually prove theorem 4.1?
By combining lemmas 5.4 and 5.5, we can demonstrate that our non-degenerate variety X, it does contain this open-dense subvariety U, and it has that coarse moduli scheme structure. It's like we're building this chain of logic step by step, using these carefully constructed lemmas as our building blocks. But remember, our goal is to understand those rational points, so we need to link U back to the world of those rational numbers.
Right. We need to bridge the gap between this abstract moduli space and those concrete solutions to equations. How do they make that connection?
That's where proposition 5.2 comes in. This proposition gives us a recipe for constructing Paršin constructions, specifically for S-integral points. Think of those S-integral points as like a generalization of integer solutions to equations. They're points on schemes whose coordinates belong to a ring associated with a base scheme S.
Okay, so it's like extending that concept of integer solutions to this more general setting of schemes and base schemes. What does proposition 5.2 actually tell us about these S-integral points?
It states that if we have a variety Y over the integers and it becomes a coarse moduli scheme over a certain ring, and if we have this closed subscheme Z within Y, then the forgetful map from the points of Y over the algebraic closure of the rationals, denoted YQ, to that moduli space of abelian varieties, denoted AGQ, gives us a Paršin construction, specifically for the points in YZ where O is the ring of integers of a number field.
Wow, that's a mouthful. So we have this variety Y with a special structure, and this proposition tells us how to build a Paršin construction based on Y and a closed subscheme Z within it. And that forgetful map you mentioned, is that just a way of simplifying things?
Yeah.
By like discarding some of the structure of a point in Y?
Exactly. The forgetful map, it takes a point in Y and it essentially forgets some of its properties. This gives us a point in that simpler space of abelian varieties. And importantly, this proposition works in both the general and Hilbert cases, which gives us some flexibility in how we apply it.
So we can use this proposition to construct a Paršin construction for UQ, a set of rational points on our special subvariety U. And once we have that construction, we can just apply Faltings' theorem to prove that UQ is finite, right?
That's the brilliant part. The proof of proposition 5.2 itself relies on some deep results from algebraic geometry. It involves concepts like état covers, moduli schemes, and those Galois actions. But the key takeaway is that we now have this powerful tool for connecting those rational points on U to those points in the moduli space. This allows us to leverage Faltings' theorem to actually prove finiteness.
It's amazing how the authors have woven together all these different threads, non-degeneracy, those coarse moduli schemes, Paršin constructions, and Faltings' theorem. And it's all to establish this profound result about the finiteness of rational points.
It truly is a symphony of mathematical ideas. And we've really only scratched the surface. There's so much more to explore, from the explicit height bounds in Corollary 5.3 to that fascinating connection between ICO models and the generalized Fermat problem.
I'm eager to continue exploring. Let's move on to those height bounds, see how they quantify the complexity of these rational points. Right, we've seen how the authors established that finiteness of those rational points on these special subvarieties. Using that ingenious combination of moduli spaces, Paršin constructions, and Faltings' theorem. But now I'm really curious about those explicit height bounds that they derive. Can we take a closer look at those?
Absolutely. That's where the power of their approach really comes through. Let's focus on section 7 of the paper, where they delve into those geometric properties of non-degenerate curves and those ICO models.
Perfect. We've been talking about ICO models quite a bit, but I'd love to get a more concrete understanding of their geometric features and how those actually lead to these height bounds.
One of the key results in this section is corollary 7.1, which really establishes this fundamental connection between integral curves and those ICO models. It states that any integral curve over those rational numbers, essentially a smooth curve without any singularities, well, it has an ICO model that's defined over the integers.
So no matter what integral curve we begin with, we can represent it using an ICO model with integer coefficients. That's a great foundation for their approach. But this corollary comes from a deeper result, right? Something about different notions of non-degeneracy.
You're exactly right. Lemma 7.7 is key here. It connects that abstract notion of non-degeneracy, in the context of moduli spaces. And it connects it to this more concrete condition, a condition involving those equations defining the ICO model.
So it gives us like a practical way to check if a curve is non-degenerate, just by examining its ICO model equations. That's much more tangible than dealing with those abstract moduli spaces.
Exactly. It basically states that non-degeneracy in that moduli space sense is equivalent to a condition on the scheme-theoretic image of the ICO model within that moduli space.
Scheme-theoretic image. That sounds a little technical. Can you break that down for me?
Yeah. Think of it as a way to capture not only the points of a variety, but also that underlying algebraic structure, the equations that define the variety. It's a more sophisticated way to understand how a variety sits inside a larger space. Lemma 7.7 says that if this scheme-theoretic image avoids certain, special subschemes within the moduli space, then our curve is non-degenerate.
Okay, so it's all about how that ICO model intersects, or rather doesn't intersect, certain bad spots within the moduli space. That makes sense. And once we have this connection between non-degeneracy and those ICO model equations, what do the authors do next?
They shift their focus to understand the properties of general ICO models. So they define a general ICO model of degree n as a curve defined by a particular type of equation within that 5-dimensional projective space that we talked about earlier.
Right, the space with that icosahedral symmetry where those ICO models live, and I'm guessing these general ICO models have some nice properties.
They do. Proposition 7.2 tells us that a general ICO model of degree n is, it's non-degenerate, smooth, projective, geometrically connected over the rational numbers, and has genus 2n plus 1, 2.
Wow, that's a lot of good news packed into one proposition. So general ICO models are, well-behaved in several ways. And we even know their genus based on their degree. That's really powerful. But how do they actually prove such a comprehensive result?
The proof involves a clever mix of techniques from algebraic geometry. They use Bertini's theorem, which guarantees the smoothness of a general member of a family of varieties. And they also get into calculating the arithmetic genus using those Hilbert polynomials. Those are powerful tools for studying the properties of projective varieties.
It sounds like they're pulling out the big guns from algebraic geometry to establish these properties. But it's all worth it because now we have this solid understanding of these general ICO models. And I'm guessing this understanding is crucial for their study of those rational points, right?
Precisely. Section 7.2 is where the rubber meets the road. They establish this key result, an effective Paršin construction. It's for those rational points of non-degenerate curves. Remember, Paršin constructions, they give us that bridge between rational points on a variety and points in a moduli space. So we can study them from a whole different perspective.
Right, like a decoder ring.
Yeah.
Translating between those different mathematical languages. And what makes this Paršin construction effective?
Corollary 7.4 states that if we have a non-degenerate curve and an open subset of that curve, defined by a non-degenerate ICO model, then we get an effective Paršin construction with some additional nice properties.
Additional properties. What kind of properties are we talking about?
Well, for one, this construction is compatible with heights. Remember we talked about how the height of a rational number measures its complexity? This effective Paršin construction makes sure those heights of the rational points on the curve are related in a very precise way to the heights of those corresponding points in the moduli space.
So it preserves that notion of complexity as we move between the world of curves and the world of those moduli spaces. That makes sense. And I'm guessing this compatibility is pretty crucial for establishing those explicit height bounds we've been talking about.
You're spot on. Corollary 7.5 brings all these threads together. It gives us this explicit bound on the height of any rational point in that open subset UQ we've been discussing. This bound involves the normalized degree of the curve, the height of the curve itself, and that quantity heap, the one we mentioned earlier, which comes from the coefficients of those ICO model equations.
So we have a formula. It tells us just how large those rational points on this special subset can get. That's incredible. It's like this quantitative measure of the complexity of those solutions.
Right.
But how do they actually prove this bound?
The proof of corollary 7.5 is really elegant. It combines that effective Paršin construction from corollary 7.4 with those height bounds from corollary 5.3, which relate to the heights of points in the moduli space. It's like a culmination of all the tools they've developed up to this point.
It's amazing how they've built this intricate framework step by step, and then used it to get to this powerful height bound. It's a testament to the power of algebraic geometry and just the beauty of those mathematical connections. And they even go further, don't they? Giving us a simplified bound for a specific case.
Yes, corollary 7.6 gives us a simplified height bound. It's for that special case where our curve is defined directly by those ICO model equations. It's a more specialized version of corollary 7.5, tailored for this specific situation.
So it's a more streamlined version, perfect for when we're working directly with those ICO models. This whole deep dive has been an incredible journey. We started with that abstract concept of moduli spaces, and now we're here, at these concrete height bounds on those rational points. It's amazing how much ground we've covered.
Yeah. It's been a pleasure exploring this fascinating world with you. The authors of this paper have made a real contribution to our understanding of those rational points and how they connect to geometry. And who knows, maybe their work will inspire even more discoveries, perhaps even an effective version of Mordell for those higher dimensional varieties.
The possibilities are truly endless when we dive into the mysteries of mathematics. Thanks to your expert guidance, I feel like I've gained a much deeper appreciation for the power and the beauty of these abstract ideas.
It's been my pleasure. Until next time, keep exploring.
Welcome to another deep dive. Today, we're going to be tackling a paper by Von and von Känel that explores a new way to understand rational points on geometric shapes. It's a bit of a mathematical treasure hunt. So rational points are those with coordinates that can be expressed as fractions. What makes them so interesting is figuring out when there's only a finite number of them on a particular shape. And this paper uses some pretty ingenious methods to do just that, focusing on a specific example called the icosahedron surface.
Right. What grabbed my attention immediately was the paper's unique approach. Instead of tackling the problem head-on, they use this clever technique called the Paršin construction to essentially shift the whole problem onto a different playing field. It's like trying to figure out how many coins can fit on a table. But instead of measuring each coin and arranging them, you figure out the total area. They could cover and compare that to the table's area.
That's such a great analogy. It makes this complex idea much easier to grasp. So they're not directly solving for the rational points, but instead they're mapping them to points on something called moduli spaces, which represent these complex mathematical objects called abelian varieties. And if they can prove there are limits on those moduli spaces, then they know there must be limits on the rational points of the original shape as well.
That's the gist of it. And what makes this paper even more exciting is how they apply this technique to the icosahedron surface. Now, as you mentioned, this surface is connected to even deeper mathematical structures, known as Hilbert modular varieties. Without getting too lost in the weeds, these varieties give us powerful tools to analyze this specific surface.
So the icosahedron surface with its beautiful symmetry isn't just a pretty face. It's actually the key to unlocking some pretty deep mathematical secrets. But before we get too far ahead of ourselves, let's take a step back. This paper starts by linking this whole exploration to something many of us might be familiar with. Fermat's last theorem.
Right. Fermat's last theorem, the idea that no three positive integers can satisfy the equation, a to the n plus b to the n equals c to the n, for any integer value of n greater than 2. This paper actually tackles a generalized version of this problem, looking at equations that have a similar structure, but plotted on more complex surfaces, like you guessed it, the icosahedron surface. These equations look more like a sub 0 times x to the n plus a sub 1 times y to the n plus a sub 2 times z to the n equals 0. It's not just about solving those equations, but figuring out when those solutions are limited.
So we're not just revisiting a classic theorem, we're actually taking it to a whole new dimension. But hold on, this mapping technique they're using, the Paršin construction, does it work for any curve on the icosahedron surface?
That's a great question, and the answer is no. The paper focuses specifically on curves that they call non-degenerate. Essentially, these are curves that have the right properties for this mapping to work effectively. Imagine trying to wrap a gift. Some shapes wrap neatly while others are a nightmare. Non-degenerate curves are like those nicely wrapping shapes in this analogy.
Okay, so non-degenerate is like a VIP pass to this mapping party. But how do we know if a curve is non-degenerate?
The paper gives us a criterion. a test we can apply to curves on the icosahedron surface to check if they meet these special requirements.
So they've given us the map, and they've given us the tool to check if we're on the right path. This is really starting to come together. They introduced this term icomodel. Can you explain what that is?
Icomodel is just their shorthand for a specific way of representing a curve on the icosahedron surface. It's like a set of equations that describe the curve within that surface's framework.
It's like a customized coordinate system for each curve.
Precisely. And they're useful because they provide a concrete way to apply these abstract mapping ideas.
Got it. So with these icomodels, they can actually start testing and analyzing different curves, see which ones are non-degenerate, and ultimately make progress on determining if rational points are finite.
Exactly. And they found that for most complex icomodels, automatically pass the non-degenerate test.
That's cool. So complexity is good in this case.
Of course. There are definitely some simpler curves that also pass the test. That's part of the fun, classifying all the curves that meet the criterion.
A challenge for our listeners. So we've got rational points. We're working on the icosahedron surface. We're using the Paršin construction to map things to moduli spaces. And we've got this non-degenerate test. What else should we be thinking about?
One more thing, the authors connect the bounds on the number of rational points to the coefficients of the equations defining the curves.
So the numbers in the equation can tell us something about how many rational points there might be? That's fascinating.
It is. They introduced this quantity called the integral degeneration, which basically measures how badly a curve can degenerate over different number systems.
Can we get a little more specific about what integral degeneration tells us?
It helps quantify the problem's complexity. The larger the degeneration, the harder it becomes to nail down exactly how many rational points there are.
Like a measure of how much chaos we're dealing with.
Exactly. And since we're dealing with equations with powers of variables, even small changes in coefficients can lead to big differences in possible solutions. The degeneration helps us track that.
By analyzing these degenerations and connecting them back to the bounds, are they able to refine those bounds?
That's the question. It's complicated. They don't completely solve the problem, but they establish some intriguing relationships.
Sounds like they're giving us a new way to think about these problems, at least.
Absolutely. And they hint at future research directions. Remember the mention of integral points. They suggest that understanding these degenerations could be key to tackling that problem as well.
Integral points, here we come. But we've got more to uncover about rational points and this icosahedron adventure, ready to dive back in.
Absolutely. There's still plenty to explore in this paper.
Okay, let's unpack one of the more intriguing parts of this paper. Their focus on a specific example of a non-degenerate plane curve. What makes this example stand out?
It's where we really see the icomodels and the Paršin construction in action. They choose a curve defined by an equation that looks like this. A sub 0 times x to the m plus a sub 1 times y to the n plus a sub 2 times z to the n equals 0. What's interesting here is that each coefficient, a sub 0, sub 1, and sub 2, is raised to the same power, n.
So there's a kind of symmetry to the equation itself.
Yeah.
But how does this tie back to the icomodels and the icosahedron?
Well, remember how we can map rational points on the icosahedron surface to points on moduli spaces using the Paršin construction? The authors cleverly choose an icomodel that directly relates to this type of equation.
So it's like the icomodel is custom designed to analyze this specific curve.
Exactly. And using this approach, they're able to prove something pretty significant. For a large class of these equations where the powers are balanced like this, there can only be a finite number of solutions where x, y, and z are all non-zero.
Wow, they're essentially solving a whole family of equations with this one technique. That's a powerful demonstration of how these tools can crack open problems in number theory. But I'm guessing there's a catch.
There's always a bit of nuance. While they prove the number of solutions is finite, they don't tell us how many. And as we discussed earlier, those bounds they get aren't exactly practical for finding all the solutions. So we know there's treasure out there, but we still need a better map to find it.
Precisely. But even knowing those solutions are finite is a major step in number theory, and it opens the door for future research, perhaps with more refined techniques to actually pin down those elusive solutions.
Okay, so we have these balanced equations, custom-made icomodels, and another proof of finiteness. What else about this example is worth highlighting?
This example beautifully highlights the connection between the integral degeneration and the coefficients of the equation. They demonstrate that the degeneration, that measure of how much a curve can misbehave, is directly related to the coefficients themselves. So the numbers in the equation actually tell us how well behaved the curve is.
That's the fascinating part. It points to a deeper relationship between the arithmetic of the equations and the geometry of the curves.
This whole journey has been amazing. We started with rational points on a surface,
Yeah.
then explored moduli spaces and mappings, and now we're digging into specific equations and their coefficients. It's like we're peeling back layers of a mathematical onion, with each layer revealing something new and fascinating.
You know, one thing that really struck me from this paper was the way they went the extra mile to make their constructions explicit. It's not just abstract theory, they provide concrete tools to work with these concepts.
You're right, they don't shy away from equations and examples. Speaking of which, let's delve a bit deeper into this non-degenerate criterion they keep mentioning. Can we break that down a bit more?
Absolutely. Not all curves are created equal when it comes to this mapping technique. They need curves that are well-behaved, which they call non-degenerate. Think of it like this. Some functions have smooth, continuous graphs, while others have jumps breaks or sharp turns. The non-degenerate curves are like those smooth, well-behaved functions in this scenario.
I see. So the non-degenerate criterion helps us identify the curves that will play nicely with the Paršin construction. But how do we actually test for this?
The paper lays out a specific set of conditions that a curve's equation must satisfy to be considered non-degenerate. These conditions relate to how the curve behaves at certain special points, and they essentially ensure that the mapping doesn't run into any roadblocks.
So it's a kind of quality control check to make sure our mapping works as expected.
Exactly. And this test is directly linked to the ultimate goal of proving the finiteness of rational points.
It feels like we've covered a lot of ground already. So we have rational points. We're working on this fascinating icosahedron surface. We're using the Paršin construction to map things to moduli spaces. And we have the non-degenerate test to help us along the way. Anything else we should keep in mind?
There's one more crucial aspect we haven't discussed in detail, the height of a rational point. This concept plays a crucial role in bounding the number of rational points, and it's deeply connected to the coefficients of the equation defining the curve.
Height. That sounds intriguing. What exactly do we mean by the height of a rational point?
Think of it as a measure of the point's complexity. A rational point's height is essentially determined by the size of the numerator and denominator in its fractional representation. Points with larger numerators and denominators are considered to have greater height.
So a point like 1/2, 1/3 would have a lower height than a point like 1234 over 5678, 901 over 1121.
That's the general idea. And what's remarkable is that the authors of this paper managed to connect the height of rational points on the curve to the coefficients in the equation defining the curve. They show that curves with larger coefficients in a specific sense tend to have fewer rational points of bounded height.
Wait, so the size of the coefficients in the equation can actually limit the number of rational points with a certain height. That's a surprising connection. I wouldn't have guessed that the coefficients could have such a direct influence on the geometry of the curve.
It is, and it's one of the key insights that allows them to make progress on this problem. By relating the height of rational points to the coefficients, they can leverage existing knowledge about the distribution of numbers to constrain the possible locations of these points.
That's incredibly clever. They're essentially using number theory to gain control over the geometry of the problem.
Exactly. And this connection between the arithmetic and the geometric is what makes this whole approach so powerful.
Okay, this is all starting to click into place. We have the Paršin construction to map our rational points, the non-degenerate criterion to filter out the well-behaved curves. And now we have this notion of height that connects back to the coefficients of the equation. It's like a multi-layered puzzle. And we're starting to see how all the pieces fit together.
And what's even more remarkable is that they managed to weave all these ideas together to prove concrete results about specific types of equations.
Like those balanced equations we talked about earlier.
Precisely. For those equations, they're able to establish specific bounds on the number of rational points of bounded height, effectively demonstrating that the number of solutions is indeed finite.
That's a huge accomplishment. It's one thing to have a theoretical framework, but it's another thing entirely to use that framework to prove concrete results.
Absolutely. And it highlights the power of combining different areas of mathematics. They're drawing on insights from algebraic geometry, number theory, and even a bit of topology to crack this problem.
This deep dive is turning out to be a true interdisciplinary adventure.
And the adventure isn't over yet. Remember that tantalizing mention of integral points? Well, those points play a crucial role in another fascinating area of number theory. Diophantine equations.
Diophantine equations. Now you're really piquing my curiosity.
Diophantine equations are polynomial equations where we're specifically interested in finding integer solutions. And as you might imagine, they can be incredibly challenging to solve.
So like trying to find whole number solutions to equations like x squared plus y squared equals z squared.
Exactly. And the connection to integral points is that if we can find all the integral points on a curve defined by a Diophantine equation, we've essentially found all the integer solutions to that equation.
That's a pretty powerful connection.
Yeah.
So by studying integral points, we're essentially tackling one of the most fundamental problems in number theory, finding integer solutions to equations.
Precisely. And what's so exciting about this paper is that it hints at the possibility of extending these techniques to the study of integral points. It's like they're opening a new door to a whole unexplored realm of mathematics.
This is all so incredibly fascinating. We've gone from rational points on a surface to moduli spaces and complex mappings, and now we're delving into the world of Diophantine equations and integral points. It's like we're climbing a mathematical mountain. And each new peak we reach reveals even more breathtaking vistas.
And the climb isn't over yet. There's still plenty to explore in this paper, and even more to discover beyond its pages.
Well, then let's not waste any time. Ready to continue our ascent.
Lead the way. I'm eager to see what other treasures we uncover.
So we've established that integral points are these fascinating objects that hold the keys to solving Diophantine equations. But how do they actually connect to the work Fan and von Känel are doing in this paper?
That's where things get really interesting. The paper itself doesn't delve deeply into integral points, but it does offer some tantalizing hints about how their techniques might be extended to study these special points. Remember how we talked about the integral degeneration?
Yeah.
Measuring how badly a curve behaves over different number systems?
Right, it was like a measure of the chaos or complexity of the curve.
Exactly. Well, the author suggests that understanding that this degeneration might be crucial for tackling the problem of integral points as well. They propose that by carefully analyzing the degeneration, we might be able to establish bounds on the number of integral points on a curve, just like they did for rational points.
So it's like they're giving us a blueprint for future research, a path forward to explore these even more challenging problems.
Precisely. And what's so exciting is that this blueprint connects seemingly disparate areas of mathematics. They're essentially saying that by understanding the arithmetic properties of a curve, as captured by its integral degeneration, we can gain insights into its geometric properties, particularly the distribution of its integral points.
That's a powerful idea. It's like they're bridging the gap between the discrete world of integers and the continuous world of geometry. But let's get back to this paper's main focus, rational points. You mentioned earlier that they were able to prove concrete results about specific types of equations. Can you give us an example of one of those results?
Of course. One of the most striking results involves those balanced equations we discussed earlier, the ones where the coefficients are raised to the same power. They prove that for a large class of these equations, there's a direct relationship between the size of the coefficients and the number of rational points of bounded height. Specifically, they show that if you increase the size of the coefficients, the number of rational points with height less than a certain bound decreases.
So it's like the coefficients are acting as a kind of control knob, regulating the density of rational points on the curve.
That's a great way to think about it.
Yeah.
And this result has some profound implications. It suggests that for these types of equations, there's a sort of trade-off between the complexity of the coefficients and the abundance of rational solutions.
That's fascinating. It's like there's a hidden balance at play in the world of these equations. But hold on, you keep mentioning the height of rational points. Can we unpack that concept a bit more? What exactly does it mean for a point to have a certain height?
Think of it as a measure of how complicated a rational point is. Remember, a rational point is simply a point with coordinates that can be expressed as fractions. The height of a rational point is determined by the size of the numerator and denominator in those fractions. So a point like 1/2, 2/3 would have a relatively low height, while a point like 1234 over 55678, 90101 over 1121 would have a much higher height.
So it's like a way of quantifying the messiness of the fractions that represent the point's coordinates.
That's a good way to put it. And what's remarkable is that this seemingly simple concept of height turns out to be deeply connected to profound questions in number theory.
I'm starting to see that. It's like this concept of height is a bridge between the world of geometry, where we visualize points on curves, and the world of number theory, where we study the properties of integers.
Exactly. And by understanding how the height of rational points relates to the coefficients in the equation defining the curve, we can gain a deeper understanding of how the arithmetic and geometric aspects of these problems intertwine.
This is all so incredibly mind-blowing. It feels like we've just scratched the surface of a vast and intricate mathematical landscape.
And that's the beauty of mathematics, isn't it? There's always more to explore, always deeper connections to uncover.
Well said. And for our listeners out there who are ready to embark on their own explorations, we'll be sure to link to the original paper and some other resources in the show notes.
Keep those minds curious and never stop asking questions. The world of mathematics is full of wonder and beauty waiting to be discovered.
Until next time, happy exploring. All right, get ready to dive deep, because today we're tackling some pretty dense math, huh? Rational points on curves and this new technique called ICO models.
It's definitely a powerful approach, that's for sure.
So what exactly is an ICO model? I mean, I remember from geometry class that an icosahedron is that 20-sided solid with all those symmetries, but how does that connect to, curves and rational points?
Well, the key is really in how these ICOs models are constructed.
Okay.
They use a special way to represent the curves, but it's within a four-dimensional space, and the symmetries of the icosahedron are really crucial in defining that representation.
So we're using a familiar 3D shape to navigate this more abstract, higher dimensional world where these curves kind of live. That's pretty wild.
Yeah, it's a really neat connection.
But remind me, what exactly are rational points? Why are they so important in this whole thing?
Well, a rational point on a curve is just a point where the coordinates are can be expressed as fractions, like ratios of whole numbers. It might seem like a pretty simple concept, but trying to understand how these rational points are distributed and the number of them on a given curve can be incredibly challenging.
Right, it's not just finding one, it's about understanding like the whole landscape of all the possible rational points. Right?
Exactly. Yeah.
And that's where these ICO models come into play.
Precisely, yeah.
Okay.
The research we're diving into is really focused on this specific type of curve called non-degenerate curves.
Okay.
And when you represent them using these ICO models, they exhibit some really remarkable properties that help us kind of unlock the secrets of their rational points.
Non-degenerate curves, that sounds pretty intriguing.
Yeah.
What makes them so special?
Basically, for a curve to be non-degenerate means it satisfies certain geometric conditions, but it's specifically within this ICO model framework.
Okay.
And what's fascinating is that this geometric property directly implies a crucial arithmetic property.
Yeah, wow.
The curve will only have a finite number of rational points.
Wait, so that's a big deal, right? Proving that finiteness of rational points for certain types of curves has been like a major challenge in number theory.
Absolutely, yeah. And what's really exciting about ICO models is that they give us a new and surprisingly elegant way to approach this problem.
So we're saying by cleverly representing this curve using the ICO model, we can essentially see the finiteness of its rational points just reflected in the geometry of the model.
That's a great way to put it.
This is already kind of blowing my mind when we're just getting started.
Yeah.
The paper also mentions a connection to this famous unsolved problem in math, the Mordell conjecture.
Right.
Can you tell us a bit more about that?
Well, the Mordell conjecture, which was actually proven by Faltings back in 1983, states that any curve with a certain level of complexity has only, finitely many rational points. But what's remarkable is that ICO models provide this fresh perspective on this really profound result.
So these ICO models, they not only offer a way to prove the finiteness of rational points for specific curves, but also potentially shed new light on a broader class of curves that are kind of encompassed by Faltings' theorem.
Exactly. And the researchers actually show how these ICO models can be used to explicitly construct families of curves that satisfy the conditions of Faltings' theorem.
Okay.
So it offers us a more concrete and visual understanding of this very abstract result.
Okay, I'm starting to see the power of these ICO models. But how do they actually work? I mean, the paper goes into some pretty heavy mathematical machinery to prove their points.
You're absolutely right.
Like, can you give us a glimpse behind the curtain?
Yeah, the researchers employ some pretty sophisticated tools, and one of the key techniques they use is something called Paršin constructions.
Paršin constructions, that sounds familiar.
Yeah.
Did you mention those earlier in the context of connecting curves to abelian varieties?
Yeah, I did. Paršin constructions are a very powerful tool for relating different types of mathematical objects. And in this case, they let us connect curves to abelian varieties, which, as we talked about before, have properties that make them easier to study.
So it's like creating a bridge between two different mathematical islands, allowing us to transport knowledge and insights from one to the other.
That's a fantastic analogy.
Okay.
In this case, the island of abelian varieties is well-charted territory.
Okay.
They have a rich structure that mathematicians have been studying, for centuries.
Yeah.
And by connecting our curves to these abelian varieties through Paršin constructions, we can actually leverage that existing knowledge to understand the curves better.
Okay, so we're using a well-studied system, abelian varieties, to illuminate this less understood one, our curves in their rational points.
Exactly.
Okay.
And this is actually where another important concept comes in, moduli spaces.
Okay.
Think of moduli spaces as spaces that parameterize families of mathematical objects.
So if I'm understanding this right, a moduli space is like this catalog of blueprints for constructing different types of mathematical objects with specific properties.
That's a great analogy, yeah.
Okay.
In this research, the moduli spaces that they focus on actually parameterize families of abelian varieties.
Okay.
So by choosing the right moduli space, the researchers can essentially narrow down the types of abelian varieties they need to consider and focus on the ones that are most relevant to the curves they're studying.
So it's like you have a giant toolbox filled with all these different mathematical tools, and the moduli space is like this filter, helping you select the right tools for the job, the ones that are going to be most effective for analyzing the curves and their rational points.
Precisely.
And to connect those two worlds, the curves and the abelian varieties, there's this technique called isogeny estimates, right?
Yes.
Now we're getting to the really technical stuff. Isogeny estimates.
Yeah.
Can you break it down for us? What are those?
Sure. An isogeny is a special kind of mapping between two abelian varieties.
Okay.
But it preserves some key structural aspects.
Okay.
And isogeny estimates let us quantify how close or similar two abelian varieties are, and it's based on the properties of these isogenies.
So it's like a measuring stick that tells us the distance between two objects in this abstract abelian variety landscape. And by understanding these distances, we can somehow translate information about the abelian varieties back to our original curves.
Exactly. It's pretty remarkable.
This is incredible. It feels like we've gone from the geometry of the icosahedron to the abstract world of abelian varieties, and somehow it's all coming together to tackle this really fundamental problem in number theory.
And we're just scratching the surface.
I can't wait to dive deeper.
Yeah. Welcome back to our deep dive into ICO models and rational points.
I'm excited to see these ICO models in action. Where do we even begin?
Well, the researchers lay out a very systematic approach, and they start with the definition of non-degenerate variety.
Right. We touched on that a little bit earlier. These are the well-behaved varieties that kind of avoid those troublesome degenerate regions, right?
Exactly. And the reason they're so important is because they lend themselves really well to these techniques that we've been discussing, like Paršin constructions and moduli spaces.
Okay, so non-degenerate varieties are our starting point, but how do we actually identify them? How do we know if a given variety is well-behaved enough for our purposes?
That's where the researchers introduce three specific criteria: GL2, H, and CH.
Okay, those sound a little cryptic. Can you decode them for us? What do those labels actually mean?
Sure. Let's start with GL2.
Okay.
This criterion applies to varieties that can be described as moduli schemes of GL2 type.
Okay, moduli schemes of GL2 type. That's a mouthful. Can you paint a picture for me? What does that actually mean for the variety?
Think of it this way. These varieties are essentially blueprints for constructing families of other mathematical objects that share certain symmetries and properties that are related to this group, GL2.
Okay.
GL2 is the group of invertible 2x2 matrices,
Okay.
which plays this fundamental role in lots of areas of mathematics.
So these GL2 varieties are like master templates, and the objects they generate are all connected by these underlying symmetries from GL2.
That's pretty cool.
What about the other two criteria, H and CH?
So H and CH deal with these more specialized types of varieties that are called Hilbert modular schemes and coarse Hilbert modular schemes,
Okay.
respectively. And these are related to number fields, which are extensions of the rational numbers.
Okay, so we're moving into even more specialized territory now. Can you give us a sense of what these Hilbert modular schemes represent? What are they all about?
They basically parameterize families of abelian varieties that are particularly well-suited for studying number-theoretic problems.
Okay.
The coarse in CH indicates that these schemes might have some additional structure or properties that kind of distinguish them from the regular Hilbert modular schemes.
Got it. So we have these three criteria, GL2, H, and CH. They help us identify non-degenerate varieties, but how do we actually use them in practice? What does that look like?
The paper provides several examples of how these criteria can be applied to specific types of varieties.
Okay.
For instance, they show that any cubic Thue curve, which is a type of curve that is defined by a cubic equation, satisfies criterion GL2.
So if we encounter a cubic Thue curve, we immediately know it's non-degenerate, according to this framework. That's handy. What other examples did they give?
They also show that any variety with a special kind of mapping called a quasi-finite morphism to a Hilbert modular variety will also satisfy criterion H.
Okay, so these criteria are like a litmus test. If a variety passes the test, we know it's non-degenerate, and that opens up this whole toolbox of techniques for studying its rational points.
Exactly. And these criteria are powerful because they allow us to connect, seemingly disparate areas of mathematics like group theory, number theory, and geometry to gain this deeper understanding of these fundamental questions about rational points.
This is fascinating. It feels like we're building this framework for classifying and understanding these varieties in this really systematic way. What's the next step in their strategy? Where do we go from here?
Well, once we've identified a non-degenerate variety, the next step is to, leverage the power of those Paršin constructions that we talked about before.
Right, those bridges that connect our curves to the well-charted territory of abelian varieties.
Exactly. And the researchers actually outline their strategy for using Paršin constructions in Theorem 4.1.
Okay.
This theorem states that if you have a non-degenerate variety, meaning it meets one of those three criteria, then there exists an open, dense subvariety that has some very special properties.
Okay, let's unpack that open, dense subvariety. What exactly does that mean?
Think of it this way. It's a piece of our original variety that is both open, meaning it doesn't include its boundary, and dense, meaning that it's spread throughout the original variety in a way that's impossible to completely separate.
So it's not just some, isolated points, but a significant chunk of the original variety that behaves in a nice way.
Exactly. And Theorem 4.1 goes on to say that this open, dense subvariety can be viewed as a coarse moduli scheme.
Another coarse moduli scheme. It seems like those are popping up everywhere.
They are, and for good reason. These schemes are incredibly useful for studying rational points.
Okay.
In this case, the theorem tells us that the objects parameterized by this coarse moduli scheme have what's called a forgetful map.
Forgetful maps. That sounds intriguing, but also a bit risky. Aren't we losing important information by, forgetting things?
That's a great question. It might seem counterintuitive, but sometimes, forgetting certain details can actually make a problem more tractable.
Okay.
In this case, the forgetful map discards some information about the objects while preserving other key aspects that are relevant to our study of rational points.
Okay, so it's like strategically simplifying a complex problem by focusing on the essential features.
That's a great way to put it. And by composing this forgetful map with a Paršinus instruction, the researchers create this really powerful tool for analyzing the rational points on our original, non-degenerate variety.
So we're seeing how all these pieces fit together. The non-degenerate varieties, the Paršin constructions, these coarse moduli schemes, and the forgetful maps all working in concert to help us understand rational points.
Exactly. And Theorem 4.1 actually highlights a particularly important consequence of this. The set of rational points on this open dense subvariety is finite.
Okay, that's huge. It means that, at least for this part of our variety, we could theoretically find all the rational points.
In theory, yes. But as we discussed earlier, actually finding those points in practice can still be, a real computational challenge.
Sure.
However, this theoretical result does lay the groundwork for developing algorithms that could, make that search more efficient.
Okay, so we're making progress on, both the theoretical and the computational front. This is exciting.
It is. And to make things even more concrete, the researchers delve into a specific case study. ICO models of curves.
Ah, yes. ICO models, that's the whole, the name of the game here. Those are the models based on the icosahedron, right?
Exactly. In this section, they focus on how ICO models can be used to study rational points on curves, which are these one-dimensional geometric objects.
So we're zooming in on a particular type of variety, curves, and using these special ICO models to explore them.
Precisely. And they start by clarifying what it actually means for a curve to be non-degenerate in the context of these ICO models.
Okay, so we're taking our, general concept of non-degeneracy and applying it specifically to curves within these ICO model representations.
Exactly. And they show that A curve being non-degenerate in this context is equivalent to it having this specific geometric property, namely that it can be embedded into the ICO model space without intersecting certain degenerate points.
Those degenerate points again. They really are the troublemakers.
You could say that avoiding those points ensures that our curves have the properties that we need to apply our, powerful tools and techniques.
And those tools lead to some pretty remarkable results. I think that's outlined in Theorem 7.1, right?
Yes. Theorem 7.1 states that any non-degenerate curve, again in this ICO model sense, has this open, dense subvariety that is itself a coarse moduli scheme.
Another coarse moduli scheme. It really seems like these schemes are the key to unlocking the mysteries of rational points.
They really are. In this case, the theorem tells us that the rational points on this open dense subvariety can be described using a Paršin construction that's combined with a forgetful map, just like in Theorem 4.1.
So we're seeing this recurring pattern here. These coarse moduli schemes combined with Paršin constructions and forgetful maps are like this powerful recipe for understanding rational points.
Exactly. And just like before, the theorem highlights this crucial consequence. The set of rational points on this open dense subvariety is finite.
Finiteness again. It's a testament to the power of these ICO models and the techniques that these researchers have developed.
Absolutely. And to illustrate the, concrete implications of these theoretical results, the researchers actually delve into a specific example: plane curves that satisfy a particular geometric criterion.
Plane curves, those are the ones that lie flat in the two-dimensional plane, right?
Yes, exactly. And the criterion that they introduce, labeled, is this condition that ensures that these plane curves are non-degenerate in the ICO model sense.
So we're taking our abstract theory and applying it to this specific type of curve that's relatively easy to kind of visualize.
Exactly. And by doing so, they arrive at a powerful result. They prove this explicit bound on what's called the height of rational points on these plane curves.
Height. What exactly does that mean in this context?
So the height of a rational point is essentially a measure of its complexity.
Okay.
Roughly speaking, it tells us how much information is needed to represent the coordinates of the point as fractions.
Okay, so a higher height means a more complex point.
Exactly. And the researchers prove that for these plane curves that satisfy the criterion, the height of any rational point is bounded by this specific formula that depends only on the degree of the curve and the coefficients of its defining equation.
That's incredible. It means that, at least for these specific curves, we have this concrete way to kind of estimate how complex its rational points can get. That seems incredibly useful.
It is. It has practical implications for developing algorithms that can efficiently search for all the rational points within a given range of complexity.
So we're bridging the gap between, theoretical understanding and computational feasibility.
Precisely. And this is just one example of how the researchers demonstrate the power and the applicability of their approach.
This deep dive has been an amazing journey so far. We've gone from the abstract concept of these non-degenerate varieties to concrete examples of how ICO models can be used to study rational points on curves, and along the way we've encountered these really remarkable results, including these proofs of finiteness and explicit bounds on the complexity of rational points. But I feel like we're not done yet. There's still more to explore, right?
You're right. In our final segment, we're going to delve into the heart of their methods and explore in a little more detail those Paršin constructions, moduli spaces, and isogeny estimates that really drive their results. We'll also see how their work connects to other areas of mathematics, including the famous Fermat problem. So stay tuned.
Welcome back to the final part of our deep dive. We've laid the groundwork, explored the key concepts, and now it's time to roll up our sleeves and really get into the nitty-gritty of how these researchers actually use ICO models to study rational points.
Yeah, I'm excited to kind of dig deeper into that technical machinery behind these results.
Yeah, so we've talked about Paršin constructions, moduli spaces, and isogeny estimates. Let's try to unpack each of those, starting with Paršin constructions.
Okay. Sounds good.
As we've discussed, Paršin constructions provide a bridge between our curves and this realm of abelian varieties. But how do they actually work? What's going on under the hood?
So at their core, Paršin constructions kind of exploit these geometric relationships between curves and certain types of surfaces.
Okay.
Imagine taking a curve and you're carefully gluing it onto a surface in a very specific way.
Okay.
The resulting geometric object can then be related to an abelian variety, which, as we've mentioned, has this richer algebraic structure that's easier to analyze.
Okay, so we're essentially embedding our curve into this higher dimensional space, and somehow that allows us to connect it to an abelian variety. But how do we choose the right surface and the right way to, glue the curve?
Right, so that's where the cleverness of this construction comes in. The researchers are very carefully selecting these surfaces and gluing procedures to make sure that the abelian variety that results really captures that essential information about the original curve's rational points.
So it's not just any random gluing process. It's designed to preserve the information we're actually interested in.
Exactly.
Okay, that makes sense. So now, once we've constructed this abelian variety, how do we actually get that information about the rational points back on our original curve?
That's a great question. And that's where those moduli spaces that we've talked about come into play.
Okay.
Remember, moduli spaces are kind of like blueprints for constructing these families of mathematical objects.
Right.
In this case, we're going to choose a moduli space that parametrizes abelian varieties with very specific properties that are relevant to our curve.
Right. So we're narrowing down that catalog of blueprints to only the ones that are suitable for our, specific construction.
Exactly. And then by focusing on those relevant abelian varieties, we can actually leverage their properties to understand those rational points back on our curve.
This is so cool. It's like this back and forth between geometry and algebra.
It really is, yeah.
We start with this geometric construction, the Potcast construction, and then we use the algebraic structure of the moduli space to gain these insights into the arithmetic of our curve.
Precisely.
Okay, I'm starting to see how all these pieces are fitting together, but we have one more ingredient that we haven't really talked about in detail yet, and that's those isogeny estimates.
Right.
How do those factor into this whole framework?
So isogeny estimates are really crucial for quantifying relationships between different abelian varieties.
Okay.
And that's within our chosen moduli space. Remember, an isogeny is a special kind of map between two abelian varieties, and it preserves certain structural properties.
Right. It's like a distance-preserving map in this abstract world of abelian varieties.
Exactly.
Okay. All right.
And isogeny estimates actually allow us to measure those distances, so to speak. They give us a way to compare different abelian varieties in that moduli space and figure out how close they are to each other.
So by understanding these relationships between the abelian varieties in that moduli space, we can somehow get information about the rational points on our original curve.
Precisely. It's like using a network of interconnected points, the abelian varieties, to kind of triangulate the location of our target, the rational points on the curve.
This is all pretty mind-bending, but I'm starting to see the elegance of this whole approach.
Yeah.
We've basically built this really sophisticated mathematical machine that lets us translate a problem about rational points on curves into a problem about relationships between abelian varieties in a moduli space.
Yeah, and that's what makes this research so powerful. By working in this framework, the researchers can really leverage this existing knowledge about abelian varieties and moduli spaces to prove new things about rational points on curves. They've shown that certain types of non-degenerate curves have, finally many rational points, and they've even come up with these explicit bounds on the complexity of those points.
And they've even applied these techniques to tackle that Fermat-like problem on the icosahedron surface.
Yeah.
It's amazing how they can extend this framework to solve problems in, seemingly totally unrelated areas.
Right. It really highlights how interconnected math is.
Yeah.
These researchers have really woven together concepts from geometry, algebra, and number theory to create this powerful and really elegant tapestry of understanding.
This deep dive has been a wild ride, but it's been so enlightening. We've gone from the basic definition of a rational point to this intricate world of ICO models, Paršin constructions, moduli spaces, and isogeny estimates. I'm kind of in awe of the ingenuity and creativity of the mathematicians who developed these tools.
I agree. It's really a testament to the power of human curiosity and our drive to understand these hidden patterns and structures in the universe.
And to all our listeners, if you're feeling inspired to explore further, we encourage you to check out the original research paper. There's a whole world of mathematical beauty waiting to be discovered.
Absolutely. And until next time, keep exploring, keep questioning, and keep diving deep